There is light in this room that is older than anything you have ever touched. Not the light from the lamp, not daylight filtering through the window. Something else, invisible, passing through the walls, passing through the ceiling, passing through you right now, without pause or resistance. Microwave photons from the earliest observable moment of the universe. Hundreds of millions of them, moving through every cubic centimeter of air around you at this moment, arriving from every direction at once, so uniform and so pervasive that they fill the entire observable universe the way water fills a glass, completely, with no corner left empty. They have been traveling for nearly 14 billion years. They began their journey when the universe was 380,000 years old, a number that sounds large until you consider that the universe is now more than 13 billion years old, and those photons have been crossing space for almost all of that time. They were released in the moment the universe first became transparent. Before that moment, everything was plasma, a dense, hot fog of charged particles so tightly packed that light could not move more than a short distance before scattering. Then the universe cooled enough for electrons and protons to settle into neutral hydrogen atoms, and the fog lifted, and the light that had been trapped inside it streamed outward in all directions at once. That is the light passing through you now. It carries the imprint of that first transparent moment. The slight variations in temperature across the sky, 1 part in 100,000, barely a whisper of difference between one direction and another, are a direct record of the density variations in the primordial plasma. A photograph of the universe as it was, unchanged by anything that happened afterward, arriving at this room and at every other room on Earth, simultaneously, patient and indifferent and extraordinarily old. Tonight, we are going to follow the universe forward from this moment, not to its current age, but much further, past the last stars, past the last black holes, into a silence so complete that it changes what time itself means, and then perhaps a little further still. Not because the story becomes frightening at its far end. It does not. It becomes something quieter than that. Something that, if you let yourself rest inside it, feels less like an ending and more like a very long, very slow exhale. The oldest light in the universe is in this room. That is where we begin. If you find these quiet journeys useful for sleep, subscribe and settle in. We are going to take our time tonight. The first fire a human being ever tended was probably an accident, a branch caught from a lightning strike, or an ember carried from a natural burn. Someone crouched beside it. Someone noticed that it gave warmth, that it held back the dark, that it asked nothing except to be fed. And so it was fed, carefully, with the patience that useful things deserve, and the practice passed forward across every subsequent generation that has ever lived. Every fire in human history has followed the same pattern. It begins with something ordered: dry wood, structured carbon molecules carrying stored energy accumulated over years of growth. It burns, it releases that energy as heat and light, and then it cools. The coals glow orange, then red, then dim. The ash is grey and cold by morning. The energy has not disappeared. It has moved outward into the air, into the ground, into the wider world, and in moving outward, it has become less available, less organized, spread thin across a larger space until it is impossible to gather back. There is a name for this in physics: entropy, the tendency of ordered systems to become disordered over time, the tendency of concentrated energy to spread. It is not a law that requires explanation in the way that some physical laws do. It is almost a consequence of mathematics, of the simple fact that there are far more ways for energy to be spread out than there are ways for it to be organized. A fire burns because the universe is doing what it almost always does, moving toward the more probable arrangement. You have watched this happen. Every person who has ever sat beside a fire has watched this happen. The coals cooling as the night deepens, the warmth pulling back, the dark moving closer by degrees. There is something in that moment, not grief exactly, but something adjacent to it. A recognition that the warmth was real, that it mattered, and that it has a direction it moves toward, A child sitting beside a dying campfire once asked where the heat goes. The adults around her did not have a complete answer, and in some sense neither does physics. Not fully, not yet. The heat goes outward. It disperses. It becomes part of the wider temperature of the air, and the air of the wider night, until the difference between where the fire was and where it was not becomes too small to measure. The universe is doing this on every scale simultaneously. Astronomers in ancient Egypt catalogued the stars overhead with the same care they gave to grain stores and flood records, because the stars were that reliable, that present, that important to the practical work of living. They listed their magnitudes and their rising times and their positions relative to each other, and they passed those lists forward to the next generation of scribes, who passed them forward again. Those lists are archaeological artifacts now, but the stars they described are still there, still burning, their light still arriving every night at the same positions, the same brightnesses, the same patient presence. Those ancient astronomers did not know they were watching fusion fires, hydrogen fusing into helium inside cores so hot and dense that the physics is difficult to imagine. They knew only that the stars were reliable, that they rose and set on schedule, that they could be counted on. What they could not have known, and what we know now, is that every star they catalogued was in the middle of the same process as the campfire, burning through its fuel, converting ordered energy into heat and light, moving slowly in the direction that everything moves. The stars they watched are older now than they were then, closer to their ends by a few thousand years, which is almost nothing on the timescales we are about to discuss, but is also real. The fire is older, the coals will cool eventually. Not tonight, not in any lifetime, or any civilization, or any era that we have words for, but eventually. That eventually is where tonight takes us, not with urgency, not with alarm, the way you might watch a fire burn down on a quiet night, resting against something solid, comfortable, not needing it to last forever. The fire has been burning for a very long time. We are going to watch it burn for a while longer, together, in the dark. The universe right now is in what astronomers call the Stelliferous era. The name comes from the Latin for star-bearing, and that is exactly what it is. A long, luminous period in cosmic history during which stars are forming, burning, and dying in numbers large enough that the universe glows from a distance. If you could somehow step outside the observable universe and look back at it, you would see a faint, diffuse light, not from any single source, but from the accumulated output of hundreds of billions of galaxies, each containing hundreds of billions of stars, all burning at once. We are in the middle of that era now, roughly halfway through it, by some estimates. Stars form from molecular clouds, enormous gatherings of hydrogen and dust, cold and dark, drifting through the spaces between existing stars. When a cloud becomes dense enough, gravity takes over. The cloud collapses inward. As it falls, it heats. At the center, where the pressure becomes extreme and the temperature climbs past 10 million degrees, hydrogen nuclei begin to fuse. A star ignites. It will burn for as long as it has fuel, and as long as the outward pressure of its burning can balance the inward pull of its own gravity. Our sun has been doing this for about 4.5 billion years. It has roughly the same amount of time remaining before it exhausts its hydrogen core and begins to change. In cosmic terms, it is middle-aged, settled, stable, reliable in the way that middle age tends to be. The larger stars burn faster. A star 10 times the mass of our sun burns through its fuel in tens of millions of years rather than billions, blazing brilliantly and briefly, before ending in the collapse that produces a supernova, and then the dense stellar remnant left behind. The most massive stars are profligate with their fuel, spending it quickly, living bright and short. The small stars are misers, red dwarfs. Stars with a fraction of the sun's mass burn their hydrogen so slowly and at such low temperatures that they glow a dim, steady red. They are the most common stars in the galaxy. They are also the most enduring. A red dwarf with half of the sun's mass might burn for 5 trillion years. One with a quarter of the sun's mass might last for 10 trillion. On timescales like those, the entire current age of the universe, 13.8 billion years, is barely a beginning. The Stelliferous era will last, in rough terms, for 100 trillion years before the last red dwarf finally exhausts its fuel and goes dark. 100 trillion years. The number is large enough that it resists the imagination entirely, and yet it is the shortest timescale we will encounter tonight. Everything beyond it is longer. What ends the Stelliferous era is not a catastrophic event. No collision, no explosion, no dramatic finale. The molecular clouds run out. Star formation requires raw material, hydrogen gas dense enough and cold enough to collapse under gravity, and over time, that material is used up, converted into stars, locked inside stellar remnants, dispersed by the energy of supernovae and stellar winds into a form too diffuse to collapse again. The last stars form, they burn, and when they go dark, there are no new ones to replace them. The universe will not announce this. There will be no moment at which a threshold is crossed and a signal goes out. The last star formation event will happen quietly in some unremarkable corner of some unremarkable galaxy, and the resulting red dwarf will begin its slow, trillion-year burn. And that will be the last the universe will be lit by the survivors, the stars already burning. And as they age and dim and finally go out, one by one, across trillions of years, the sky will become a little darker each time. Ancient astronomers kept their star catalogues with care, updating them across generations, correcting positions as instruments improved, adding newly observed objects, and removing ones that had been misidentified. The lists were living documents, passed from one set of hands to the next, refined by each generation that held them. The stars they recorded are still there. The tradition of recording them is still there. There is something in that continuity, the list longer now than it was then, the stars still burning, the work still ongoing, that is worth sitting with. The universe is in its bright era, the era of fires burning across 100 billion galaxies, of light crossing distances so large they have no everyday equivalent, of energy moving outward from millions of stellar cores, every second of every day. That era will last for a very long time. And then, slowly, it will begin to end, not in any way that would be visible to a single observer, not in any way that would register as an event, but in the way that all gradual things end, which is one dimming at a time, over longer stretches than any mind has yet found a way to hold. After the last star goes dark, the universe does not become empty. It becomes a different kind of full. What remains are the remnants, the dense, cold objects left behind when stars exhaust their fuel and the burning stops. White dwarfs, the cores of stars like our Sun, compressed to roughly the size of Earth, glowing with residual heat but no longer fusing anything. Neutron stars, the collapsed cores of larger stars, so dense that a teaspoon of their material would weigh more than a mountain. And black holes, the gravitational endpoints of the most massive stars, and of the enormous accumulations of matter at the centers of galaxies, where millions or billions of solar masses have collapsed into objects so compact that nothing, not even light, can escape their pull once it has crossed the boundary. The white dwarfs cool. Over quadrillions of years, they radiate their remaining heat into the surrounding space, growing dimmer and dimmer until they become what physicists call black dwarfs, cold, inert, dark. Objects that emit no light, generate no heat, do nothing except drift through space under the influence of whatever gravity remains to pull them. No black dwarf has ever been observed, because the universe is not yet old enough for any white dwarf to have cooled that completely. They are a future object, something that will exist in eras we will never see. Then there is the question of the protons. Ordinary matter, the atoms that make up every planet, every star, every piece of everything is built from protons and neutrons at its core. The proton appears, in everything we have observed, to be stable. It does not decay. It does not spontaneously break apart. And yet some extensions of our current understanding of physics suggest that it should, very slowly, on timescales so vast that every proton that has ever existed in the history of the universe would still be intact today, even if the decay rate were real. physicists have built enormous underground detectors, tanks of water surrounded by sensors in the quiet dark below mountain ranges, specifically to watch for a single proton decay. They have been watching for decades. They have not found one. Whether protons eventually decay or persist indefinitely is a question that remains genuinely open. It matters because if they decay, all ordinary matter eventually dissolves into radiation over timescales of perhaps 10 to the power of 36 years. If they do not, the cold remnants of stellar history drift on, essentially forever, through a universe growing steadily darker and quieter. Either way, the black holes remain. Black holes do not evaporate quickly. They evaporate with a patience that makes every other timescale we have discussed seem frantic by comparison. The mechanism was described by Stephen Hawking in 1974. Near the boundary of a black hole, quantum effects allow particle pairs to briefly appear from the vacuum, and occasionally one particle falls inward while the other escapes outward. The escaping particle carries energy. The black hole, over unimaginable time, loses mass. For a black hole with the mass of our Sun, this process takes roughly 10 to the power of 67 years. For a supermassive black hole, the kind that sits at the center of a large galaxy containing billions of solar masses, the evaporation takes closer to 10 to the power of 100 years. That second number is so large that comparing it to the first is like comparing the current age of the universe to a single second. And the current age of the universe, by that point, would itself be a duration too small to bother measuring. Right now, somewhere in the universe, a photon is escaping from a black hole. Hawking radiation is happening, particle by particle, photon by photon. Some black hole is losing a fractional amount of mass, an amount so small it would require instruments we cannot build to detect. But it is happening. The physics is patient in ways that nothing in human experience has prepared us to appreciate. There have been many generations of physicists who worked on these questions, who sat with the equations, who built the detectors, who watched the underground tanks for any sign of proton decay, who developed the mathematics of Hawking radiation, and then argued about its implications across decades of papers and conferences. They passed the questions forward the way the ancient astronomers passed their catalogues forward. Not finished, not resolved, but carried carefully from one set of hands to the next. The questions are still being carried. Eventually, in the long, slow fullness of 10 to the power of 100 years, the last supermassive black hole completes its evaporation. There is a final burst of radiation, brief and brilliant compared to everything that preceded it. As the black hole's mass drops low enough that the evaporation accelerates, and the last of it disappears in a flash of high-energy photons, and then the universe contains no more black holes. What remains is radiation, photons, neutrinos, gravitons, particles of light, and the nearly massless messengers of gravity and the weak force, all expanding outward through a universe so vast and so empty that the average distance between any two particles is, for all practical purposes, infinite. The energy of each photon has been redshifted by cosmic expansion until it is effectively zero, not absent, but so dilute and so cool that the distinction barely matters. Fire is out, every fire everywhere is out, the ash is cold, and the universe continues expanding still into distances that no unit of measurement we use has the capacity to describe. Dark, patient, and, in a way that takes some time to recognize, extraordinarily interesting. Here is something that takes a moment to settle properly. A photon, a particle of light, does not experience time. Not in the way a moving clock runs slow, not in the way that time passes differently near a massive object. Those are relativistic effects, real and measurable, but they are still effects experienced by something with a clock, something with mass, something that accumulates duration. A photon has none of that. From the mathematical framework of special relativity, a photon traveling through a vacuum accrues exactly zero proper time between any two events on its path. It is emitted, it is absorbed. In between, from the photon's frame of reference, if such a thing can be said to exist at all, nothing passes. no duration accumulates. The journey from a star 4 light-years away to the back of your eye takes 4 years in your frame of reference, and no time at all in the photons. This is not a loose metaphor, it follows directly from the equations. What it means in the far future of the universe is this: after the last black hole has evaporated, and all massive particles have either decayed or annihilated, everything that remains is photons and gravitons, and the lightest possible things. Particles traveling at or near the speed of light. And in a universe made entirely of such things, there are no clocks. Not misplaced clocks, not broken clocks. The physical conditions that allow clocks to exist have ceased to apply. A clock requires a massive object moving along a trajectory through space-time, accumulating proper time, changing state in a measurable and repeatable way. A pendulum swings, an atom oscillates, a quartz crystal vibrates. All of these require mass, and mass requires the right conditions to exist, and those conditions, in the universe's final state, are no longer present. Without clocks, time as a physically meaningful quantity loses its grounding. The equations still contain a time variable, but that variable no longer refers to anything that could be measured inside the universe. It becomes, in some sense, a coordinate without a referent, and something else disappears along with the clock's scale. Measuring distance, at its most fundamental, requires timing, a signal sent and returned, a wavelength counted, an oscillation compared to a standard. All of these require clocks. And if clocks are gone, the physical content of distance measurements goes with them. You cannot say, in a universe with no massive particles, that one thing is larger than another, not in any way that can be physically verified. Every length scales together when you apply what mathematicians call a conformal transformation, and the physics is unchanged. The big version and the small version of the same radiation-filled universe are for all purposes that matter identical. No experiment performed inside either one could tell them apart. Polynesian navigators crossing the Pacific used stars the way we use instruments, not because they understood the nuclear physics of stellar interiors, but because the light was there, and it was consistent, and it was enough. The photon arrived regardless of whether the navigator understood it. The light served its purpose without requiring explanation. In the far future universe, the photons are still arriving, still traveling, still carrying whatever they carry. But there is no one to navigate by them, and more than that, there is nothing to define what direction means, what distance means, what size means. The universe has become, in the precise language of mathematics, conformally invariant. A state in which scale has no physical grounding because there is nothing left to define it. Now hold that alongside something else. In the very earliest moments after the Big Bang, before the first fraction of a second had elapsed, before the Higgs field had settled into its current configuration and given particles their masses, the universe was also in a state where mass played almost no role. The temperatures were so extreme, the energies so high, that even particles with rest mass were moving fast enough that their mass was negligible compared to their kinetic energy. The physics of that moment was approximately scale invariant, approximately conformally invariant, two states: the far future, cold and empty and radiation-filled; the early universe, hot and dense and radiation-filled, both approximately scale invariant, both existing in a regime where the concept of size has no firm anchor, both described in the mathematical language of conformal geometry. A geometry that pays attention only to angles and the shapes of light cones, not to distances and volumes, in structurally similar ways. This is not a poetic observation, it is a geometric one, and it is the foundation of a serious proposal in theoretical physics, that these two states, which look like opposites in every ordinary sense, may be mathematically equivalent in the precise technical sense. Equivalent, way that allows the far future of one universe to be continuously connected, through a conformal boundary, to the beginning of the next. The light navigators trusted crossed oceans it could not understand. Perhaps, in some sense that mathematics is only beginning to make precise, it is still crossing. There is a surface at the edge of the universe's future. Not a wall, not an edge in the physical sense, nothing you could approach, nothing with a texture or a temperature. A geometric surface in the mathematical sense, a boundary that the structure of space-time approaches as the universe expands and cools and empties toward its final state. Mathematicians have a name for it, the future conformal boundary. And what makes it interesting, what makes it more than a technical term, is what the geometry of that boundary looks like when you examine it carefully. If the universe reaches its final radiation-dominated state cleanly, if all massive particles have gone, if only light and its near-massless relatives remain, expanding through a space with no structure and no scale, then that boundary is smooth, not broken, not singular, not a place where the equations fail. A smooth surface with a well-defined conformal geometry, carrying encoded within its structure the entire history of everything that ever happened in the universe it closes. A smooth surface can be connected to another smooth surface. This is where a proposal by the mathematician and physicist Roger Penrose becomes something more than speculation. Penrose spent decades working on the geometry of singularities, the places where space-time breaks down, where curvature becomes infinite, and the equations of general relativity reach their limits. He proved, with Stephen Hawking, that such singularities are unavoidable under very general conditions, and then he turned his attention to what those singularities actually look like when examined in the right geometric language, not the ordinary language of distances and volumes, but the conformal language of angles and causal structure. What he found, or rather what the mathematics suggested, is that the Big Bang singularity, the beginning of our universe, may not be a genuine physical breakdown at all. It may be a conformal boundary, a smooth surface if one specific condition is met, that the curvature of space-time at the beginning had a particular form, vanishingly small in the specific sense that physicists call Weyl curvature. The Weyl curvature measures the tidal, shape-distorting aspects of gravity, the kind that builds inside black holes to extremes. At the beginning of the universe, the evidence strongly suggests it was close to zero. If both boundaries are smooth, the future of one universe, the beginning of another, they can be identified with each other. The infinite future of a dying universe, conformally compressed, becomes the beginning of a new one, not through any dramatic physical process, not through a collision or an explosion or a bounce, through a geometric continuity. The way two pieces of smooth cloth can be sewn together at their edges. What crosses this boundary is radiation, only radiation. Every massive particle, every atom, every stellar remnant, every black hole that spent 100 trillion years evaporating has already converted its mass into radiation by the time the boundary is reached. The Hawking radiation from the last evaporating black holes joins the general bath of photons already filling the universe, and the whole structure expands to the conformal surface and continues through. On the other side, a new universe begins. Not the same universe, not a repetition of the same events, a new one starting in a low entropy state, ordered, structured, with a thermodynamic arrow of time pointing forward, because the geometry of the conformal transition forces it to begin that way. The very specific initial conditions that made our universe capable of forming stars, planets, and everything else would not be a lucky accident in this picture. They would be a geometric consequence, an inevitability written into the shape of the boundary. Whether this is correct remains genuinely open. The proposal makes a specific prediction that the gravitational wave bursts from massive black hole mergers in the previous universe, compressed through the conformal boundary, should leave faint circular imprints in the cosmic microwave background. Rings of unusually low temperature variance left the way. A heavy object leaves a mark in soft material without intending to. Penrose and collaborators have looked for these rings and found candidates. Other physicists, using different methods, have found the same patterns, consistent with what ordinary cosmology would predict. The question is not settled. New instruments are being built. Satellite experiments designed to map the microwave background with a precision that current tools cannot reach. They will look, among other things, for exactly this kind of imprint. The answer may arrive within a decade or two, or the data may remain ambiguous, and the question will be carried forward again, as it has been carried before. For now, what is certain is this: the universe's far future and its beginnings share a mathematical character that no one had reason to suspect until the geometry was examined carefully enough, and the light that crosses the space between them, the radiation that survives the conformal boundary, if the boundary is real, is not young light. It is light that was present in a universe before ours, carrying nothing deliberate, addressed to no one, but carrying, in the faint statistical texture of its distribution, the unintentional record of a cosmos that burned and cooled and finally, quietly, handed off. The oldest light in the universe may be older than the universe. That is not a conclusion. It is a question held open, the way the best questions are, not with urgency, but with patience, with the particular kind of patience that the universe itself seems to have in unlimited supply. Every fire that has ever burned was part of this, not metaphorically, in a direct physical sense. Every campfire, every candle, every star in every galaxy in every direction you could point was drawing from the same reservoir of ordered energy that the universe began with. That extraordinarily improbable, extraordinarily structured initial condition from which everything since has been slowly, patiently unwinding. The heat that moved outward from a fire 10,000 years ago is still moving. Dispersed, diluted, spread across volumes no instrument could gather back. But present, energy is conserved. It does not disappear. It changes form, it spreads thin, it becomes less available for doing anything organized. And that spreading is what entropy measures, what the arrow of time follows, what every fire and every star and every cooling coal enacts in miniature. If the geometry holds, if the mathematics of conformal boundaries is correct, if the transition is real, then that energy does not stop at the boundary. It crosses. In a different form, carrying no memory of what it was, addressed to no one, it becomes part of the radiation that seeds the next beginning. Perhaps that is what every fire was always doing. Not ending, passing on. A child once asked where the heat goes when the fire dies. The full answer turns out to be outward, always outward, following the direction that everything follows. And if the geometry is right, then at the very end of the very end, outward leads somewhere, not back to the same fire, somewhere new, lit from the ash of what came before. It is enough, perhaps, to rest inside that possibility, not to hold it as certainty, which it is not, but as one of the things that serious mathematics has found at the edge of what can be asked. The universe may not simply stop. It may, in some geometric sense that no ordinary language quite captures, continue. The question can wait for morning. It has waited longer than that before. Somewhere tonight, someone is sitting beside a fire that is burning down. The coals are orange. The warmth is still present, but pulling back by degrees, the way warmth always does. Outside the circle of light, the dark is patient and still. Above, if the sky is clear, the stars are there. The same stars that were there for every other fire, on every other night, in every other place that people have gathered around heat and light since before anything was written down. The light from those stars left its source years ago, or centuries, or in some cases millions of years. It has been crossing space ever since, indifferent to whether it would be seen, indifferent to whether the eye that receives it understands what it is. Ancient peoples sat beside fires exactly like this one and looked up at exactly these stars and felt, in some version of the same feeling, the particular quality of a clear night and a dying fire and a sky full of patient, reliable light. The warmth of fires those ancient people tended has long since dispersed into the air and the ground and the wide dark beyond. But the light from the stars they watched is still arriving. The photons that left a star 1,000 years ago and fell on the upturned face of someone sitting in the dark, tending a fire, wondering. Those photons were absorbed, their energy transferred, their journey ended, But the star is still sending more. The light is still crossing the distance. What was present then is still arriving now. And what is arriving now will still be arriving long after every fire currently burning has gone cold. Nothing is lost, exactly. It changes, moves. It disperses into forms that are less organized, less available, less warm. But it continues in the way that energy always continues, following the direction that everything follows, outward and onward through a universe that has more room in it than anything that has ever existed can begin to fill. The coals cool. The ash is cold by morning. The light from the stars is still crossing. Every generation that has looked up at a clear night sky has looked at the same stars, slightly older, slightly different in their positions due to the slow drift of proper motion across centuries, but recognizably the same. The constancy is real. The light is real. The long continuity of people sitting beside fires and looking up is real. And you are part of it right now, wherever you are, in whatever kind of dark surrounds you tonight. The fire and the stars are the same process, observed at different scales and different speeds, both burning, both patient, both in their own time cooling and in cooling, passing their energy forward into the wider space, where it continues its long outward movement indifferent and unstoppable into whatever comes next. Rest here for a while. The stars are where they have always been. The dark is the same dark. The light keeps arriving, somewhere at the edge of the observable universe. A star is burning. It has been burning since before the Earth existed. Its light has been crossing the space between us for longer than life has been present on this planet. It does not know it is being considered tonight. It simply burns, patient, steady, converting hydrogen into helium in its core, releasing light in all directions at once, including this one. A photon from that star is crossing the dark right now. It has been crossing for a very long time. It will arrive eventually, somewhere, at a detector, at an atmosphere, at the surface of something, or it will keep crossing through an expanding universe, redshifting as it goes, its energy dropping, its wavelength stretching, until it joins the general bath of ancient light that fills all of space equally. The oldest light in the universe is passing through this room right now. You are resting inside it. The light keeps crossing.